So what we're going to talk about today is linear transformations. I think it's 0.8. Looks like. How many of you have ever heard this terminology before? Linear transformation. Quite heard the word linear, quite heard the word transformation. How do they tie together? This is going to be a central piece of a lot of what we do. How many of you are familiar with what a matrix is? It turns out that in most cases, with linear transformation is very intimately related to matrices, and we'll see how that connection works in a moment. How many of you know what a function is? Right? You all work with these all over the place in calculus, right? You looked at lines, parabolas, y equals sine x, e dx, things like this. You did fancy things. You did derivatives, integrated, and perhaps. Linear transformations are just functions. Why do we call them linear transformations? Because they're not just any functions. They're nice functions that have some nice properties we'll talk about. So here's my opening. We can act on vectors. By act, I mean we can do something to a vector by multiplying them by an appropriate matrix. What do I mean by appropriate? I mean it's got to be the right size. So for example, an input vector Z, an output a vector AB for a matrix. So suppose I have this vector. By the way, this is a 3x1 vector, so this is something in R3, right? I don't know much, but I know that if I want to act on this by a matrix, if I want to multiply by a matrix, my matrix better have how many columns? It better have 3 columns. That's the only way I can multiply. Right? So let me come up with we do a 4x3. 1, 0, 3, 4, and 1, 2 months. Now, if I take my input vector ABC, then the size of my output vector should be 4x1. Everybody agree with that? And let's see what we get. If I multiply this row times this column, A, 0, C, so I get A plus C in the top. I get 2A, I should spread this out, 2A plus B plus C, and I get 0A plus 3B plus 4C, and I get A plus 2B minus C. So for example, 1, 0, 0, if A is 1 and B are both 0, then that gives the vector 1, 2, 0, 1. Everybody agree? This is a way that I can, this is like a little magic box. You input a vector and it barfs out a new vector for you. For example, this is used in engineering, science, economics, and my favorite, television. How many of you have ever watched a movie or something on your smart TV? Have you ever messed around with the size of the picture? You know how you can go to the settings and it'll give you these different things. That's essentially what's going on here. maybe your movie is a box like this, but you want to watch it widescreen, because it's Stanley Kubrick, right? How do you spread this out, right? Well, your vectors in this direction stay about the same, but maybe you double the size this way. Right? So basically, I want to increase the vectors here and just a little bit up and down. Right? Really, what's happened, even though you don't know it, is the vectors in your original movie were hit by a matrix and spread out into different things so that you can have your widescreen view. So this stuff is used all over. So notice that if I call this A, going back to my example here, and I call this X, call that vector X, then this is a function. My input is the vector X, in this case ABC, and A does its little magic to it, and it barfs out this vector, 4x1 vector, that has this formula. This is the way the formula is. Right? This is a function, right? Like you're used to in calculus. You input something, you get a well-defined output for it, right? So let me give you some terminology before we can kind of get into fun stuff. I'm going to start the function now. T from Rn, or I'm sorry, Rn to Rn. Has input from Rn. So this is like my function. My input is Rn, and my output is in Rn, right? The place that I'm getting my inputs from, anybody know the fancy word for your inputs for a function? I bet you know this. Domain. Y'all know that one? Rn is called the domain of the function. And it's basically all the garbage that you can plug in. Right? Your outputs are in Rm. Anybody know what the output place is? Right, you hear that word a lot. I'm gonna use a different word and I'm gonna distinguish it from range. This might go. This is called codomain. Or target. Some people call it target. Right, looks like a target. It's got an arrow pointing at it. Right. How many of you have heard the term range before? Okay, I'm gonna distinguish that, and I'll give you an example that shows the difference. The collection of all P of X as X varies through the domain is called the range. Now, by the way, before I do the example, does anybody see the subtle difference between codomain and range here? Yeah.
So the codomain is all the R of M, but you may not necessarily be able to get all of them.
That's exactly right. Everybody agree with that? The codomain of this is Rm. This is the target, is where I'm trying to go. The range is everything that can be hit by this. There might be some stuff that I don't touch over here. Let me give you kind of let me give you an example that's like more from calculus. So this is kind of a function that you would have seen in calculus here. And in calculus, you almost always study real functions. This is a function from the reals to the reals, right? When you plug in x, a real number, sine x is a real number. Everybody agree with that? What is the range of the function? Let me remind you that sine x is something like this. Yes.
-1, 1.
That's right. I mean, if you ever put a number in your calculator and take the sign of it and it says 2, it's time to throw the calculator in the trash can, right? Because the output of sine is everything between 1 and -1, and that's it, right? So the range of this is -1 to 1. Now, here, the way that I've listed this function, the codomain is R. I could have also written f is a function from R to -1, 1, right? This is also true. In this particular case, now the codomain and the range are the same thing. So it's a matter of definition when you start off, what are you shooting at? Everybody okay with it? So yeah, it's just a matter of definition there. Let me give you another example here. I'll give you another one where the range of the codomain is different. Let's look at the following function. Consider the following example. Want the function and here's what I'm going to do here. The way I'm going to define this function is when I input the vector x, I'm going to multiply it by the matrix A. And I'm going to tell you what the matrix A is. It is going to be this. Okay, so let's see what happens. Let's kind of look at what this does. The domain here is R3, and the codomain is also R3. So I input a 3x3 vector. This is a 3x3 matrix. I input a 3x1 vector. This is a 3x3 matrix. I put in a 3x1 vector, and I get a 3x1 vector. Right, so it's going to R3. Everybody okay with it? Let's see how it works. That's going to be 3A, 0, and 2B. Can somebody, so let me ask you this first question. Is the range and the codomain the same for this particular? Can somebody tell me, how can you tell?
You're never gonna get anything that's outside of a certain plane because
That's right. No matter what, no matter what vector I put in there, what can you say about the second coordinate of the output? It's always zero, right? So the range can't be everything because in R3, you certainly, would everybody agree, you've got the vector 0, 1, 0. No way are you ever getting that, right? So the range here, let's say alpha 0. In fact, you can make any vector like this. So in particular, the range is alpha anything is a linear combination of these two vectors. Okay. Okay, any questions? I'm gonna do another one of these matrix multiplications. Let's do this one. Okay, fine. Make a new function. Here's another example. Let's let I'm gonna work the and I'm gonna play with this because I think we can kind of try to visualize this one. I want T of X, A of X, where here A is the matrix 1, 0, 8, 2, 1. This is called a shear transformation, right? Now, I can write a formula for what happens here. Let's see. Okay. Okay, what's my output? Notice this time this is X minus 2X. Everybody see that one? Is everybody clear on how I got the X and the minus 2X plus 1? So what does this do? Actually, it's kind of interesting because when you input a vector, it leaves the first coordinate alone, right? But it does some kind of yin yang to the second one, right? It takes -2 times the first coordinate and adds it to the second. So maybe to get a picture of this, and this is kind of like my TV set. Well, my broken TV set, perhaps. What does this do? The unit square. So let me draw a square here. So this is vector 0, 1. This is vector 1, 0. So my big question is what does this linear transformation do to this square? Right? Just forget about everything else because it did square. Well, let me collect some data here. See if we can kind of follow this. what does it do to, is that one? What does it do to 0, 1? Let's kind of run some tests over here. Let's see. So I can use this formula. And what do I get? I get 0 and I get 1. How about that? Left it alone. Everybody agree with that? So this stays the same. So I'll put a number, Roman numeral 1 here. That's where it is. Right? Okay, this one's trickier. How about 1, 0? Well, let's use the formula because I didn't bother to write it up. See, x is 1 and y is 0, so it should go to 1, -2. Right? So it took this vector, which I'll put Roman numeral number 2 here. See about that. Let's see, what was it? 1 over 1, -2. So let's see like that. So notice basically what it did is it kind of squeezes down here. Huh. Okay, here's another one kind of for perspective. By the way, what's this vector right here that I've drawn the diagonal? What's that vector? Correct. This is the vector 1, 1. Let's see, I'm going to call this Roman numeral number 3. Let's see what happens to that. And curious. Okay, so now both x and y are 1. So we'll see, what do I get? I get 1, -1. Agree? Okay. So this is over. So it's the same export as this, only it's down half as much. So this is the vector 3, 1. By the way, what does it do to the 0 vector? Okay. It leaves it alone. It gets the 0 vector back. Huh. So what do you think this looks like? I think this looks like a parallelogram, doesn't it? It looks like, I mean, the only thing that we've got is this kind of dotted line here and this dotted line here, right? So I would guess if I call this Roman numeral 4, it should connect the tip to the tip like this. So this should be 4, right? And this should be 5. So it turns, this is called a shear. Notice what happened to this thing. Well, what it looks like happened to this is this was twisted down in a parallel fashion. So it's basically like you took the bottom and you shifted them both down, and this moved down with it. Everybody agree with that? Now there's one missing piece of the puzzle. I was real hand-wavy about this. How can I verify that in fact this connector right here, this 4, is actually what came out of this here? How can I verify that, right? I mean, I just said, oh, look, the tip of this, the tip of that. I thought I connected them in a straight line. How do I know it's not like this? Right? How can we check that?
I need to check every point in between this.
What an ambitious fellow he is. You want to check it, but actually he's exactly right. I mean, what we can do is we can basically check every point between there. So let's do that. And I'll leave 5 to you guys because it's actually easier. We'll do the 4 and I'll show you that it connects up. Okay. So on line 4, this is the horizontal line here. Can you describe what the vector looks like along the tips of this? So you can think of this vector moving from here to here, right? So if I want to describe domain 4, well, it's going to have 2 coordinates. But there's one of them that's easier than the other. What can you say about the y coordinates on here?
It's one.
They're always 1. Everybody agree with me? So the vectors, as we sweep across there, should always have y coordinate 1, right? And of course, you can kind of see this because at the start, it's got y coordinate 1. At the end, it's got y coordinate. And everywhere in between, it's got y coordinate 1. Okay, so far? What about the x coordinate? Well, the x coordinate is just x, right? I mean, because that's going to change. Everybody agree with that? But I can say that x is between what?
0 and 1.
And as x varies between 0 and 1, then you get all those vectors, right? Everybody okay with that? I mean, you might think of this as just kind of sweeping by. The arrows kind of move as x varies from here. Everybody agree with me? Now, let's take our linear transformation and see what it does. What does t do to the vectors? Well, t of x1 is equal to a of x1 everybody agree with me? So let's multiply this out because I erased my formula. Ding dong. This is x, and this is minus 2x plus 1. Everybody okay with that? Now this is a little bit harder to see than the previous one because I've got moving x, I've got a moving first coordinate, moving second coordinate, right? Everybody agree with me? But can somebody tell me how we can get what this should describe? This should describe the 4 in codomain. How can I do that? What does, so what if I got x 1 minus 2x? What does this describe? What points in the plane does this describe? Well, think of this. I mean, if you were to draw this vector, this would be your x coordinate, which I'll call x. It's between 0 and 1. And this would be your y coordinate. Agree? So doesn't this mean that your y coordinate is 1 minus 2x?
Yes.
And what is that?
That's it.
That's on y. This is y equals 2x, where x is between 0 and 1. So notice that when x is 0, y is 1. So it starts at this vector here, and it ends up when x is 1, y is negative 1. So it ends up down here, and the tip of the vector moves along the line y equals 1 minus 2x. And if you check these points here, that's y equals 1 minus 2x. Everybody okay? And you can check this as well. And this, I hope this helps to demonstrate what I've kind of been trying to convey to you all a little bit. If you think about it carefully, math is checkable, right? There's many, many kind of ways to do this and sort of verify that what you've got is correct. Okay, any questions on Okay, here's another one. It's just kind of fun. How many of you have had Cal 3? Smattering. I mean, how many are going to have Cal 3? The ones of you that took Cal 3 are going to, you've seen, do you remember changes to polar coordinates when you were doing multiple integrals? Well, you can also do, you do polar coordinates, elliptical coordinates, a lot of it. The following example kind of motivates this. Looks like T go from square to our square. I want T vector V be AV, where A is so this one, in a certain sense, you might think, well, junior weights are tunnel, it's pretty easy, because if you look at T, X, Y, this is A times X, Y. So I get 2X, 3Y. So basically, what this function does is it pushes the X coordinate out to double its size. And it pushes the Y even more. It pushes it to 3 times the size. So it's pushing out X, it's pushing out Y, but it's pushing the Y a little bit harder. Everybody okay with that? Question: what does this do? You might want to take this.
Would it make it an ellipse?
Very good. It does. It actually makes some lifts. And it's more stretchy this way than this. Let's see what happens to this. Let's take an E of XY. This is pushing this out 2X, 3Y. But for convenience, I don't want to confuse myself too much here. I'm going to add new variables here, S and T. So 2X is S and 3Y is T. Now notice so in my new coordinates S and T, notice that X is 1/2 S and Y is 1/3 T. Everybody agree with that? And so let me point out that X squared plus Y squared, that's 1/4 S squared plus 1/9 E squared. But X squared plus S squared is also what? It's also 1, right? Because X and Y sit on that circle, so X squared plus Y squared is 1. That means that in my new coordinates, S squared, X, we have S over 2 squared plus T over 3 squared equal 1. So as you said, this is an ellipse. It goes something like this. This is 0.03, this is 0.20. So see what we've done. Now this transformation, which is a fairly simple matrix, this says stretch my X coordinate by 2, leave everything else loose, stretch my Lockhorn by 3, leave everything else alone, and I take a circle to an ellipse. This is actually very useful in doing coordinate changes to multiple intervals, among many other things. So it's not just TV. Okay. Any questions? Okay, so I've given you a number of examples. I gave you that shear where we found that the square turned into the parallelogram. We saw the circle stretch into an ellipse. What my examples had in common was I'll define the function by multiplying by a matrix, right? So let's see what happens with that kind of thing. So let's suppose P is a function from Rn, Rm. Okay, so this is a generalization of my last examples. I want to find a function that takes Rn, so my input is an n-dimensional vector, my output is an m-dimensional vector. And I want A to be a matrix. What size is, I know I'm beating you on this, what size does my matrix have to be? Does it work? Good. Actually, n by n. Because I want to multiply this by an n by 1 vector. And then its output, so let me kind of put this parentheses here. I want to multiply this by an n by 1 vector and get an n by 1 vector. Everybody okay with that? Okay, so let's suppose that we have this function that's defined by multiplying our vector by a fixed matrix. Let me point out a couple things that happen that is extra super really cool. If you look at P of u plus b, so what happens when I plug in u plus b to this function? This is the matrix A times u plus b, correct? Anybody guess the next step I can do to simplify, perhaps? I can multiply this out. This is something I learned about matrices, right? This is AU plus AB, but this is equal to so in other words, evaluating the function of the sum of two things, you can evaluate it separately and then add them up later. This is not true for most functions that you've ever encountered. This is not true for sine x, right? It's not true that sine of 1 plus sine of 2 is sine of 3. You can't do that, right? But with this kind of function, you can. And there's another glorious benefit. If you have a constant, then you can pull it. This is A times CU, which is CAU, which is CD. So you can pull a constant out of it as well, right? So these functions that you get just by taking an n-dimensional vector multiplied by an n by n matrix and getting an n-dimensional vector, these have a couple of nice properties. These kind of properties are not true in general for most functions, but they are true for this. And this is a linear transformation. So this brings us, we've been doing linear transformations all day, but here is actually a function b from Rn to Rm is a linear transformation if it satisfies these two problems. Number one, E of U plus V equals TU plus TB for all U, V, and Rn. And number two, P of Cu is CTU for all C and R and U and R. So if you could break down the sums like this, and if you could pull constants out, it's a linear transformation. So any function that is obtained by multiplication by a matrix is a linear transformation. Okay. Any questions? So this is what it means to be a linear transformation. It mimics the function of multiplying by matrix. And actually, it's going to turn out, rather surprisingly, perhaps, that we've already done it. That's kind of cool. I mean, we're actually, we need to kind of show you that we're at the apex, but it turns out that this is an example of a linear transformation. It turns out these are the only examples. So if you have an Rn, so if it's finite dimensional, so you've got an Rn, every linear transformation can be written as a matrix. And we're going to talk about how we do that. Theorem. If T from Rn to Rm is a linear transformation, then number one, T of C1 U plus C2 B is C1 DU plus C2 DB. U B. Notice all this is saying is that, what have I done? I've written this as the sum and pulled up constants all together instead of doing them one step at a time. Right, okay, well, this is pretty easy to see. What happens when I plug in the zero vector to a linear transformation? You always get zero vector. Notice this is a zero vector in Rn, and this is a zero vector in Rm. Right, so they might be different sizes, but they're both zero vectors. Is it clear on this? Right, this isn't true for most functions. If I walk up to you on the street, it's not even true for most lines. If I give you the line y equal x plus 1, if you plug in 0 for x, you don't get 0 for y, right? Why is this true for linear transformations? Anybody see why why this is true? Well, let me point this out. Quite agree with that? No matter what C is, no matter what V is, this is true. Now take C 0. This is, if C is 0 here, what's 0 times any vector? It's a 0 vector. And here, TV is a vector, what's C times that vector, it's the zero vector, right? I almost feel dirty, like it's something naughty here, but that's really true, right? Because of that property, when you plug the zero vector, you always get the zero vector. Okay. Any questions? Maybe one more. This is kind of a fun thing. Do kind of one more to think about. On the road here. Yes. And I'm gonna P of B equals A B, where A is this matrix. So let theta be some fixed number. Describe what this transformation does. Let me make an observation first. You get what looks to be death on a hot plate here, right? You get x sine theta minus y cosine theta, x cosine theta, plus y sine theta. Agree with that? So, let me ask you this. My input vector xy, I drew a picture of it. It's got some x coordinate here, some y coordinate here. How would I figure out how long that vector is from your experience in trigonometry? X squared plus y squared. The square of the length, right? So would everybody agree that what's the length of this vector? Oh, look at that, huh? Well, let's check it out. Things like this, let's square these and see what we get. We square root of it, right? What happens if I square this? It's x squared times square theta minus 2xy sine theta cosine theta plus y squared cosine squared theta. That's the square of the first. Agree? What's the square of the next? X squared cosine squared theta plus 2xy sine theta cosine theta plus y squared sine squared theta. Agree? What happens when you add this up?
Yes.
Oh, it's a bloodbath, baby. These two are dead. But what happens when I add these two? Sine squared theta plus cosine squared theta. Cosine squared theta plus sine squared. And what is cosine squared theta? One. This is a miracle, isn't it? Take the square root of this, and the length of the new vector has not changed. So my challenge problem to you for next time is, can you figure out what this linear transformation is? All right, we'll pick it up there next time. Any questions? All right, I'll see you guys on Friday.